Okay, so welcome to Earth and Space Science, Geology 110. My name is Dr. Michael Keinerling. I teach physics here and geology and general science and stuff. So this class has technically three parts. Where you are right now, this is the lecture. Lecture meets Tuesdays and Thursdays from 8:30 to 10 a.m. in this room. And that's the primary place we're going to cover material. Additionally, on Tuesdays from 10:15 to 11:45, after the lecture, we will have a lab. We're not going to have a lab today because we're not going to cover enough material for the first lab. But in general, we'll have labs unless we're having a test or something. And I'll put up announcements if we're not going to have a lab. But because lab is after class, that should be straightforward. Additionally, there is what's called a supplementary instruction. This is only an hour long. It meets on Fridays from 10 to 11 a.m. This is going to be review and stuff with David Hamish. And also, this is where you're going to take your quizzes for this class. So there's going to be quizzes on each chapter. You'll take them with David. Your name? Willie. Angular materials? Yeah. So that is where you're going to take your quizzes. So you do need to go there. You can check the schedule on Blackboard. It will tell you when all the quizzes are going to be. Most of the quizzes will be in SI, well, with two exceptions, which will be on Blackboard for scheduling reasons. My office hours, if you want to get in contact with me and ask me questions, are Monday and Wednesday from 12 to 1:30 p.m. and Thursdays from 10:15 to 11:45. Also, generally, Monday through Thursday, I will be around this part of the building because I teach all my classes in this room and I'm here Monday through Thursday. So you can probably just find me. My office is, if you continue down the hall, you came in here down this hall. Down at the end of the hall, there's some windows. At the windows, if you turn left, right around that corner is my office. And that's room 335. So that's where you can find me if during my office hours generally. And David will go over how to find him, but he's in the library because he also runs the library, as well as teaches some science courses. Yeah, so that is the schedule for this class. So for this class, you're going to need a calculator. You need a scientific calculator. For tests and quizzes, we have calculators I can loan you. For homework and other stuff, you can use your phone, you can use Google, things like that. The homework will all be online. So you can use like Google as a calculator. That'll cover pretty much all you need. This I copied from another class, so this is showing more than you actually need for this class. You really just need like square roots. I mean, there might be one problem with the but you don't need a lot of calculator stuff for this class, but I copied it from another class. But I will have calculators to loan out if you need them for tests and quizzes. It's helpful to have one on your own. A basic, good scientific calculator isn't that expensive. You can just get like a TI 30 something. That's what we're handing out. So the questions for exams are based on, and quizzes are based off material drawn from the textbook, physical science. So read the textbook, you'll get an idea, do the homework, it will help you. Also the stuff that we cover in lecture. So you need to attend class, you need to keep up with the material. Additionally, Attendance cards is part of your grade, so you need to show up. You can work with each other on homework, though some problems will have the numbers randomized. Not so much in this class. Your name? Nathan. Nathan, last name? Yeah. Ah, okay. Yes. Oh. You can work with each other on homework, things like that, and labs. Obviously, you should not be working with each other on tests and quizzes. But so this class, your grade is split up in, technically this class is two classes. There's a lecture class and a lab class. You will get separate grades in lecture and lab. It's possible to pass one and fail the other. Or no. In general, so for the lecture, you have exams and quizzes. That's about 60% of your grade. You have homework, which is about 30%, and attendance is about 10%. Your grades will all be up on Blackboard. The class is curved. So don't panic if your grade is a little lower. It's basically impossible to pre-apply a curve into the Blackboard calculation, so the curve will be applied afterwards. So the grade you see on Blackboard will not be curved. I will be using a curve to determine what letter grade you get from that percentage. Your lab grade is 8 to 9 labs at 25 points each. The way labs work is you'll have a lab. We'll do a lab activity in class, and there'll be a worksheet, and then you'll have a week to finish the worksheet and turn in the lab the next week. So basically, you'll do the lab part, and then there will be extra questions and stuff. And if you don't get those all finished during the lab, or if you want to go home and do them on your own time, you can do that, but it needs to be turned in the next week. That's the way labs work. So for every lab, you'll have a week to get them, you'll have at least a week to get them done. And answer all the questions and stuff. And it's important you turn in your labs, because they count as part of your grade for the lab. And if, you know, the secret to doing decent in this class is to do all the work. Now, I accept late work. Late work will be accepted, but there will be a penalty. In general, it's going to be 10%. It can be up to 15%. Now, for labs, during the lab late, I'll just mark you down when I'm grading the lab. For homework is all going to be online. I'll go through how that works. But when you're doing homework, if the homework assignment is past due, there will be a button that you can press to request an extension that will automatically give you 2 more weeks and a 10% penalty on any work you hadn't done yet. So the way the penalty on the homework works is it only applies the penalty to work you do after the due date. So if you got the homework like 80% done and had a few questions left, definitely get the extension, because the penalty is only going to apply to those questions you did after the due date. It's not going to affect anything you did before the due date. If you can't make it to class, please send me an email. Let me know. Several people in this class have been very good about that. And for attendance, if you let me know that you're going to miss class, I will excuse your absence. It won't cost you, it won't penalize your grade for missing class. And if you do miss class, all the lectures for this class are recorded, being recorded right now, and will be posted up on Blackboard so you can watch them at a later date. I post copies both directly from Zoom and on YouTube. So you'll be able to watch the lectures. Also, if you're reviewing, you can go back and check things from the lectures. They'll all be recorded. And I generally get them up the same day as the lecture, but it's not, it takes a little while for them to process things. But homework is on webassign.net, which is Cengage, the publisher of this book's online homework system. Oh, this has a typo in it. But so I will show you how this works. So what you do is you go to Blackboard. So if you're on Blackboard, this is Earth and Space Science. I'll pretend to be a student. You can see here, there's this section. So if you need to see the syllabus or the schedule for the class, that's right here. If you need to see any of the lectures or the slides, they're all here. All the slides are here. Here are the recordings from last semester. I will start putting up the recordings for this semester after today. I gotta hide those. But homework is in the homework and ebook section. And you should be able to just click on this link and it will take you to Cengage. If you already have a Cengage account, you can just sign in with your Cengage account. If you don't, there'll be a prompt to make one. You don't need a special code for the class or anything. You just need to sign in the first time through Blackboard. That's how it's being associated with the class. And then I'm going to stop being a student because when I try and do that as a student, it glitches out on me. And then on Cengage, once you've got Cengage set up with WebAssign, view as a student, you'll see something like this. So here's the first homeworks. You can see they're due Friday next week. I've generally set homeworks to be due on the day of the quiz for the chapter. And then there's this getting started. I would suggest you start with the getting started with WebAssign homework. That is a very easy thing. It's just teaching you how the system works, how to enter answers and things like that. If you go into any assignment, so I'll start with the getting started with WebAssign assignment. You'll see there's this button here for requesting an extension. So you can request an extension. You have two options, manual and automatic. If you choose manual, I would not choose manual. If you choose manual, it sends me an email and then I have to manually give you an extension. This can take a while because I have to notice the email and things. But if you do automatic, you will get an automatic extension. Now, automatic extensions are only available for past due assignments, so I can't actually show you how it works right now, but it's really just a button that says request an extension. And you'll get 2 weeks with a 10% penalty on work you haven't done. And if you go back to the main section, you'll see how there's current assignments. There will be a button for past assignments, which will have the past due assignments in it. And when you look at past assignments, there's a request extension button next to them. So you can do that as well. Again, I can't demonstrate it right now because there aren't any past assignments. But that's how that works. If you have any questions about that, feel free to stop by and see me. If you have any trouble getting into the online homework, feel free to stop by and see me. But you do need to do the homework because it's 30% of your grade. So I am going to sign up. Now here's the schedule for the class. So we're going to start, we're going to cover chapter 1, which is sort of an introduction to science and aspects of that. And then we're going to move on to geology. So we'll go through chapters 21 through 23, which are geology. So we'll cover various geology things. After we finish geology, we'll have our first test. You can see here on 21 through 23. Then we'll move on to meteorology, which is chapter 15, 19, and 20 is what we're covering for meteorology. And then we'll have a test on those chapters, and then we'll move on to astronomy. So we're working our way outwards. And astronomy will be chapters 16 through 18 at the end of the semester. What? Oh, these are just listing the Mondays that start the week. That's why it says week out. That's okay. I basically copied it from another class. Yes, these are listing the Mondays that start the week. I should maybe change that on Blackboard. But yeah. So these are the Mondays at the moment. And you can see when you have quizzes over here, they're listed when various quizzes are. And the chapter 23 quiz and the chapter 15 quiz will be online. For scheduling reasons. So that's the schedule. We generally have a lab for every chapter, roughly. Yeah. Any questions about any of this stuff about how the class works? If you have any questions later, feel free to just ask. If you're having any trouble with like the online homework, ask, and let me help you get it set up. Because it's an important part of the day. So we're going to start talking about measurement and an introduction to the earth sciences, because that's what we're going to be covering in this class. So the book covers all the physical sciences, but this class covers earth sciences. If you want to cover the other physical sciences, that's a different class. You use the same textbook for two classes. So what we're going to go over, we're going to go over the areas of study within earth science, including astronomy, meteorology, and geology. We'll talk about the earth systems, the four earth systems, the geosphere, the atmosphere, the hydrosphere, and the biosphere, and how they're interrelated. We'll talk about the scientific method and the processes involved in the scientific method, and how experimental situations are set up. We'll talk about the difference between scientific theories and laws, which is a subtle difference. And it's not that one is better than the other. They cover different things. We'll talk about the difference between independent and dependent variables. We'll differentiate between the concepts of mass and weight, which are in fact different things. We'll talk about calculations involving density. We'll look at the common measurements used in earth science and the units involved, the SI units that are used with these measurements. We'll go over the whole SI unit system. We'll talk about how to perform conversions within the metric system, how to perform calculations with scientific notation. We'll talk about the difference between accuracy and precision for measurements, and how to use significant figures to represent the precision of a measurement, and how to use significant figures in calculations to have the right number of significant figures. So how to round off calculated answers to the correct number of significant figures. So this is sort of a tree showing the sciences. The sciences can be sort of split into the social sciences and the natural sciences. The social sciences be about people. The natural sciences be about, the natural world. And the natural sciences can be split into the physical sciences and the biological sciences. The biological sciences go glorp. They involve living things, and then there's the physical sciences. And the physical sciences, the main physical sciences are things like physics, chemistry, and the ones we're going to study in this class, astronomy, meteorology, and geology, which are earth and space sciences. So here's a short video showing an introduction to earth science. So Earth science can be broken down into 5 major areas of specialization, and we're gonna look at 3 of those. These are astronomy, the study of things beyond Earth's atmosphere, meteorology, the study of Earth's atmosphere, and geology, the study of the structure of the Earth itself. So, the study of things beyond Earth's atmosphere is astronomy. Here's sort of introduction to what you're dealing with. He's covered a huge amount of material because it's everything above Earth's atmosphere. So, really, the entire universe. That's the thought. other two things we'll be studying are meteorology, which is the study of the forces and processes that cause the atmosphere to change and produce weather. So it's the study of weather and the processes involved in it. And geology, which is the study of the minerals and rocks that make up the earth and the processes that form and change these minerals. And also the history of the planet that's recorded in these minerals and rocks and various life forms. So, but that didn't do what I was supposed to. Approximate them. And then we're working with approximate inputs, which give us issues with outputs. Yeah. And geology is the study of the earth beneath us and the processes that create it. Yes. in order to understand things about the universe, we need to be able to communicate our ideas with other people. And in general, we need to measure things out in the world so we can try and understand how they work. And so extremely sophisticated methods of measurement have been developed. We can measure all kinds of things like movement, temperature, weather conditions, time, etc. And we're going to use lots of measurements throughout this book. And one of the things you might ask is, can everything be measured with certainty? And there's actually an answer to that question. It's a resounding no. It turns out that as we started measuring smaller and smaller objects and interacting with smaller and smaller objects, it became apparent that the act of measuring something involves interacting with it in some way. And that process will fundamentally change the thing you're interacting with. Basically, if you're talking about where something is located, to see something, you have to bounce light off of it. But if you bounce light off of something, the light causes that thing to move. So that's sort of the issue. Like, the process of measuring things changes them. So there's a limit to how accurate measurements can be. And this is actually like mathematically formalized in the Heisenberg uncertainty principle. Well, you don't need to worry about that. But there's actually like a fundamental limit to how accurate you can measure things. So when you deal with very small objects, there's limits. And then there's sort of limits, there's practical limits about the metrologists can do insane levels of accuracy these days. So here's a video sort of showing the scales of various objects, from the very big to the very small. So it's going to start off with larger objects. We're going to go zoom out and see the scale of various objects throughout the universe. And there'll be units down there telling you, the size of what you're looking at. And then we'll look at the very small objects. So here, the scale of buildings. Now, at a fundamental level, measurements are kind of the basis of scientific investigation. They let us share information with other people, and other people will know what we saw because we have some sort of reference to share. We observe various phenomena. This results in questions about how or why these phenomena occur. We try and build tests to figure out how and why these phenomena occur, or to test our ideas about how and why these phenomena occur. And this process of testing all of your ideas about why something happens is the modern scientific method. That the basic idea is you ask a question and then you design a test for it. So if you want to see it at sort of like the most basic, watch Mythbusters. Mythbusters boils the scientific method down to its most basic. They have a question or a thing they think might be true, and they test it. And sometimes they go back and redo their tests and see that they made a mistake in the past, things like that. So the scientists assume the universe is orderly and can be understood, and that we can make predictions about what will happen in the future by studying what happens now or happened in the past. And the scientific method is this general method of making observations and rules for reasoning and making predictions. It's a way of building understanding by, well, from a philosophical level, it's based off radical doubt. You never assume that you know anything unless it is held up by experimental evidence. And the process can be broken down into basically 4 steps. You make observations and measurements of the world. You build a hypothesis. You ask a question about those observations and measurements, and you propose an explanation. Then you do experiments to test that proposed explanation. And if that explanation holds up to repeated experiments, it becomes a theory. There are also laws, which are different from theories. Theories are an explanation for how or why something happens. Laws are a description of something that happens. You can also build up to form a law from experiments, but that's the general idea. So in general, you observe and collect quantitative data using the senses along with the existence of technical instruments, because your senses are fallible. The main reason for this is that you have this amazing brain that is really good at processing information and does all kinds of processing of information to get you useful information to keep you from being dead. This is not a good setup for recording things in a perfectly accurate and repeatable process. And also, technical instruments allow us to go beyond what our senses can see. We can use like a microscope to see things that are very small. We can use measurement tools to measure at a scale that we can't see, but the tool translates it to a larger scale that we can, things like that. And they can help us overcome the weaknesses, the issues with our senses. And, it allows us to go beyond things like optical illusions and all those other things. Because we have these really great brains that can do all this stuff, but they're never turned off. And sometimes you want just, you don't want to have many intermediate steps. So like, that's why a photograph is better than a drawing of what you saw at some level, because a photograph is going to record without intervening steps and is going to be less likely to be confused. So the senses are things like sight, hearing, smell, taste, and touch. And the primary senses we as humans use are sight and hearing. That's just the nature of humans. And for doing science, you can use all 5. So smell and taste, I really wouldn't suggest most of the time. There's some scary stories about old chemists, like, why are you tasting the mercury compounds? And we can help reduce the limitations of our senses by using measuring devices, using rulers, using calipers, using various other measuring devices that help us be more accurate. And instruments extend our ability to measure and learn about our environment and make even more precise measurements. And our senses can be deceived. So a quick example, when you look at the sun and the other stars in the sky, the sun looks huge, and the other stars in the sky are all look to be about the same size. They're just points. But the sun is actually smaller than most of the stars you can see in the sky. And is only huge because it's so close to us. It's a middling sized star, middling to small. And most of the stars we can see in the sky are big and bright. And all the stars in the sky vary dramatically in size, and that's because, but they all appear to be points, and that's because they're all so far away. So here's an example of the sizes of various stars, as allowing you to see just how different they can be. And it's going to start with, I believe, well,
On a clear night in the country, if you're lucky, you can see maybe 3,000 stars, but that's just the tip of a vast cosmic iceberg. In our galaxy alone, there are over 100 billion stars. And in fact, there are over 100 billion galaxies in the observable universe. There are more stars than there are specks of sand on Earth.
Every star is powerful, creating the basic matter for everything in the universe, including us. Most are so far away we know little about them. But there is one star that's really close, and virtually everything we know about stars we've learned from that neighbor.
The sunlight from our sun that bathes us and warms us every day is nothing but starlight, because our sun is nothing but a star like all the rest.
Seen from Earth, our sun is a blinding ball of light. But take away the glare, and one of the most powerful objects in the universe appears in our own backyard. It's a ball of superheated gas that's been lighting our solar system for 4.6 billion years and dominates all life on Earth.
The sun is 93 million miles away, and that means in actuality it's immense. You could fit 1 million Earths inside the sun.
It's over 1 million kilometers in diameter, yet our sun is tiny compared to the really big stars out there. Eta Carinae, over 5 million times larger than our sun. Betelgeuse, 300 times larger than Eta Carinae. If it was our sun, it would reach as far out as Jupiter. And then there's this monster, VY Canis Majoris, the largest star ever discovered, 1 billion times bigger than our sun.
So yeah, our sun is nowhere near the biggest stars. So we start with measurements. We measure various things. We observe the universe. We have units that we use to share information with people. Then once we have measurements, we have ideas about what we've seen. We've put together a hypothesis, a possible explanation for what we see. An example of this could be matter consists of these small particles, atoms, that simply rearrange themselves. This is an idea that's been around for literally thousands of years. But didn't really get formalized until a few hundred years ago. And this is a tentative answer, an educated guess. And to be useful, a hypothesis or a model, an explanation needs to be testable. So you may have heard of string theory. The problem with string theory is that it wasn't testable. And that's why it's basically dead. So if you have a model or an explanation for what's going on, you have to be able to test it. Otherwise, it's not useful. You have to be able to make predictions that you can test. And so what you can do is that new experiments get designed to test the validity of this hypothesis. This can be going out and making more observations, or it can be setting up a controlled experiment in a lab. Depends on what you're looking at. You know, if you have a hypothesis about stars, you can't build a star in a lab and test that. You have to go out and look at various stars. Now, but if you have a hypothesis about, you know, carbon or something, you can study that in the lab. And the hypothesis is supported if it correctly predicts the experimental results. So does your model, your explanation, predict what happens in the experiment? If yes, good. If no, you need to go back and build a new one. And you need to design your experiment such that it always can prove you wrong. That's good experimental design. So experiments are testing under controlled conditions to determine whether your results support or confirm your hypothesis. And if you're doing experiments right, your results should be not only confirm your hypothesis, but your experiment can be repeated by other people and they can do the same thing, get the same, and come to the same conclusion. And other similar experiments come to the same conclusion. And this is some sort of organized procedure that involves making observations and measurements to test a hypothesis. And when you do an experiment, sometimes you can repeat an experiment with slightly better design, and that can change the results. That happened in the field that I was studying for my PhD, where one of the first experiments that set off a lot of the interest in this subject was repeated with a new design cell that had like no gap. There was a gap that they got rid of. And that gap had something in it. And when they got rid of this gap that it filled with material that they thought was unimportant, it turns out what they were seeing went away. So what they were seeing was happening in the gap and not in this porous glass that they thought it was happening. Which killed one of the big hypotheses for that field. Luckily, I also disagreed with that hypothesis, which was great because that was right before I had to defend my dissertation. Now, when you do an experiment, you can talk about an independent variable and a dependent variable. And this terminology is a little bit confusing, but the basic idea is that the independent variable is the variable that you control. It's not dependent on anything in the experiment. It is controlled by you. This is your input at some level. This is what you as the experimenter are controlling. So it is independent of what's going on. It's what you're controlling. And the dependent variable is dependent on the independent variable. So the independent variable is basically your input. The dependent variable is basically your output. So for example, when I was doing my research, my independent variable was generally temperature. I was varying temperature. And my dependent variable was, the output I was looking at was something new, resonance frequency of this oscillating object. And I was looking at how that changed with temperature. And that was, making conclusions about other things from that. But what I was measuring was this resonance frequency, how this thing naturally oscillates. And for certain experiments, especially if you have something that's sort of a binary, you want to check whether this does something or doesn't do something. It's very important in things like drug testing. You use something called a control. And a control is really just, you do the experiment over here, you add stuff, or you do your thing, or apply your procedure, and over here, you do nothing. You just want to show that the result you get isn't being caused, wouldn't happen on its own. That's what controls are for. Controls are a way to show that the result you're seeing wouldn't happen on its own. So, if you have some sort of if you're testing a drug and you want to show that this drug makes mice get better when you give them some disease, you need a control group where you don't give them the drug to show that the mice wouldn't just get better on their own. So that's the idea of a control. A lot of time when you're varying something like an independent variable, the control is sort of your 0 point. It's the measurement where you do nothing. And when you make a graph, usually the independent variable, the variable you control, gets put on the x-axis, and the variable you measure gets put on the y-axis. That's usually the case. There's a lot of different ways you can graph things, but in general, the x-axis is what you are, as the experimenter, are controlling. The y-axis is what you're measuring. So the independent variable goes on the x-axis, the dependent variable goes on the y-axis. So here, the independent variable here is time. How long do I let this thing run? And the dependent variable is the temperature it's at. So what's being controlled by varying time is probably the amount of chemicals involved in this chemical reaction, which is why the temperature is dropping, and then as the chemical reaction proceeds, and then the temperature goes back up once the chemical reaction is over and it's absorbing heat from somewhere else. And that's a possibility. Oops. So during a scientific experiment, you record all your data very carefully. These days, it's usually done by computers, which is much more convenient than trying to do it by hand. And then once an experiment is complete, you build graphs, tables, and charts to display the data. The main way we display data in the scientific community is graphs. Lots of graphs. Share graphs with other people. And often what you do is that you have a graph of what you saw in your experiment, and you have a graph of what your model predicts, and you show that those two graphs match. And that is your argument for your model is correct. And then these data are analyzed so that you can draw a conclusion. So you also spend a lot of time looking at graphs and graphing things in slightly different ways to see if you can find patterns. And ideally, your experimental results can be duplicated by other researchers. This has been a big problem with the people trying to do superconductors these days, because there's been a lot of people doing really sketchy stuff with that. But yeah, so ideally your experimental results can be duplicated by other researchers. And in general, no concept or model of nature is valid unless the prediction is in agreement with experimental results. And ideally it should be able to be replicated by other people. Now, when scientists talk about a theory, what they mean is some sort of tested explanation for a broad segment of natural phenomena. An example of this is atomic theory. That hypothesis we talked about earlier, that stuff is made of atoms, the atomic theory has withstood testing for 200 plus years. We had to expand because we eventually figured out that atoms are also made of stuff. But in general, as long as you're just doing chemistry, atoms are not going to change to other types of atoms, so they're just rearranged. And depending on continued experimentation, theories can be accepted, modified, or rejected. So, you know, it used to be thought that there was this aether that light traveled through, and then there was an experiment done by Michelson and Morley that showed that there couldn't be an aether. Like the observations of the speed of light, depending on direction, showed that there couldn't be some medium that the Earth was traveling through that carried light. And so this aether model for light got rejected and was followed up by Einstein with the special and general theory of relativity to explain the phenomena that they saw. So, yeah, this stuff gets, theories evolve. And like atomic theory has evolved. We realize that atoms, yes, stuff is made of atoms, but atoms are also made of stuff. And you can sort of work your way down to, there's about a dozen fundamental particles that stuff is made of. And most stuff, everyday stuff, is made of like wheat. Now scientific laws. Scientific laws are, instead of an explanation of how or why something happens, they're a description of what is happening in some particular case. So after a series of experiments, you get some sort of concise statement in words or math that describes a fundamental relationship of nature, like the law of conservation of mass, which is there is no gain or loss of mass during a chemical reaction. That's tied to atomic theory, because during a chemical reaction, the atoms just rearrange, no matter is added or removed. This states the finding, but it doesn't explain the behavior. And actually that sort of got expanded with E equals mc squared, which is the understanding that mass and energy are kind of the same thing. That has to do with relativity. So here's a short video about the difference between a theory and a law. And generally these days, the term law isn't used very often. It's all on older things. People don't like that term anymore because, you know, people are people, and so there are always opinions and friends. Here's a short video about
Scientific theory versus scientific law. It is important to understand the similarities and differences between a scientific theory and a scientific law. Both scientific theories and scientific laws describe something that has been observed in nature. They both require many observations and experiments, and they both must be accepted by the majority of the scientific community. However, scientific theories are not laws, and they are not treated the same as laws. Unlike a theory, where evidence changes, a law will never change. In science, a theory is a widely accepted explanation supported by abundant scientific evidence. Theories are not just ideas or guesses about how something works, and theories are not just opinions about a concept. For science to prove a theory, scientists must conduct extensive tests and experiments. A theory must be supported by tremendous amounts of scientific evidence, and it must go through peer review and retesting. Even if a theory is proven, it is subject to change in the light of new evidence. This is the best way for science to evolve and change. In this way, scientists can use theories to build upon the evidence and ideas of other great minds. One good example of a theory that has evolved over time is Newtonian mechanics, first theorized by Isaac Newton in the 1600s. This theory explained the movement of objects, both on Earth and in space. Using Isaac Newton's work, Albert Einstein perfected the theory, renaming it the theory of special relativity. Einstein's new theory put a twist on the Newtonian theory, allowing us to measure objects in reference to space and time. Einstein even upgraded his special relativity theory to a more current version that we use today, the theory of general relativity. Scientific laws are different from scientific theories. A scientific law is a description of a fact that is completely accepted in the scientific community. A scientific law does not change, and if it is refuted, not only does the law become false, but all science that was based on that law also becomes false. Laws state that something in the natural world happens, but they do not necessarily explain how or why. The law of gravity, for instance, states that all objects have a force of attraction for each other. This law explains what happens, but not how it works or why. Theories attempt to explain the how and why. When trying to decide if something is a scientific law or scientific theory, ask yourself this question: does it explain what happens, or does it explain how and why something happens? If it explains what happens, you are talking about a law. If it explains how or why something happens, you are talking about a theory.
So this is sort of a scientific method. You make observations and measurements. You develop a hypothesis or possible explanation. You do have experiments to test that hypothesis, and you build a theory, which is a well-tested explanation. Then you build on that with more observations and measurements, and it's a cycle. And science builds on previous discoveries and refines and develops new models based on previous theories. So often, a lot of the time, you find some situation where your theory breaks, and then you need to develop a new theory that under normal circumstances gives you what you would expect, because it's not like all those observations of how things work day to day went away, but explains that weird extreme situation. So that's kind of what general relativity did. Under normal circumstances, it gives you Newtonian gravitation, but under the extreme circumstances of stronger gravity, higher speeds, greater accelerations, it explains the phenomena that didn't fit in with Newtonian gravitation. When we communicate results, we use graphs. In line graphs, you compare two variables. The independent variable gets placed on the horizontal axis, and the dependent variable is placed on the vertical y-axis. So x-axis is independent, y-axis is dependent. So here, you're controlling the temperature, and what is varying is the volume. So you're measuring the volume of this thing as you vary the temperature. And then you can find a trend, and it turns out there's a straight line that fits your the data, actually for, any gas. Another way you can communicate results, if you want to show about like portions of things, you can look at a fixed quantity using slices to represent parts of the whole with a pie graph. So this is, an example of Texas weather deaths from 1998 to 2005 and the various causes thereof. You can see the big causes are flooding and extreme heat, while, high wind, winter storms, lightning, tornadoes, they all have less. You can also look at bar graphs to talk about quantitative data that happens in chunks or happens in categories, but doesn't this is when things are grouped into different groups, but it doesn't make sense to talk about them like they're on a continuum. So, this is, flood, lightning, tornado, hurricane. And then this is comparing different things like weather fidelities for 2013, the 10-year average and the 30-year average. You can sort of see how things are changing by looking at the individual bars. And that is where I wanted to get to for today. So if you're having any trouble signing into the homework system, just drop by and ask. It should be pretty straightforward. You should just be able to click on that link. If it's not working for some reason, I'll make another link. I'm going to do that anyways. There's another link that might work. So I'm going to do that right now. So let me quickly. So this here, the Shipman Introduction to Physical Science, may also work. But I would suggest using this one because this is the first one that got created, and I think it's the one Cengage wants you to use.